In this lesson, we're going to examine what happens to a bolt that is undergoing a combined load. And what that means is the bolt is experiencing both tensile stress as well as compressive stress. Now, it's very important that we understand exactly what tensile and compressive stress means before we get into the full analysis of what happens to this bolt, and also to understand why it's undergoing a combined load in the form of tensile stress and compressive stress. So as a quick recap, if this diagram in blue represents our bolt, then what we're looking for if we're analyzing its tensile stress is the force would be acting perpendicular to our surface area right there. So that shaded region, that's representing our area in question, and our force would be pulling in either direction, equal and opposite force, just as you see up top. And that force will cause the bolt or the system to stretch in either direction. Hence, we have a tensile load there. Now, if we were to change that direction of the force up, and let's say our force was doing this instead, then we would maintain the same area, but instead we would classify this type of force as a shear force because it's trying to cut across the cross-sectional area of our bolt. So when we analyze this system, we're trying to identify where our forces will be parallel and perpendicular to the surface area in question. So since we know what the diameter of the bolt is, we can now go ahead and evaluate the cross-sectional area of the bolt. So the area of the bolt is 113.10 times 10 to the negative 6 meters squared. So that's going to represent the area of the bolt, not just for the shear stress, but also for the tensile stress. So now if we analyze the system that we have up top, let's now see how our forces are distributed. So we have this 11 kilonewtons, and it's stretching the system, so we can agree that that would induce some form of tensile stress. Now, that 11 kilonewtons, it is an horizontal force, so you can imagine that it is going across the entire system like that. And what we're going to do, we're going to break this up into force components. So if I'm to draw an axis along the length of the bolt, just like that, then that axis would represent one force component of our 11 kilonewtons, and that force component will be perpendicular to the cross-sectional area of the bolt. So if I'm to do the opposite of that, which is to draw another axis like that, and that axis, it will be the one that's parallel to the cross-sectional area of the bolt. And these two would interact at an angle of 90 degrees there. So one will be parallel to the cross-sectional area of the bolt and one will be perpendicular. So now what we need to do, we need to recognize here that this will form indeed a right angle triangle. So what we need to recognize is anywhere along that gray area that I'm just shading in now, anywhere along that gray area, we will have that horizontal force of 11 kilonewtons acting. So what we can do then is recognize that the longest side of our right angle triangle that we form here, that will represent 11 kilonewtons. So what we can do is go ahead now and break this up into the two components that we need. One for the shear force, which I'm just going to write that in as Fs for shear force, which will be this component here. So that's that component, so Fs. And then the other one for the tensile force, which I'm just going to write that here as Ft. So what we need to work out now is the force for our shear stress and the force that represents our tensile stress. So let's work those out now. So if we do Ft for our tensile stress, Ft will be opposite to this 50 degrees angle that's formed right there. So we're going to use the opposite side for Ft and the hypotenuse side, which is representing the 11 kilonewtons. So this is what we'll have then for that unknown Ft side. So it's just going to be force sin angle, just as we've done before with force components. And our force is 11 kilonewtons. So it's 11 times now by 10 to the power of 3. And sin, our angle, is 50 degrees. So the force component there for our tensile stress is going to be, so that's 8.43 times 10 to the power of 3 newtons. And let's go ahead now and evaluate our shear force component. So it's going to be a similar calculation, so Fs for shear force. And once again, it will be force, but this time cos angle. Now, as you can see on our triangle, if Ft was our opposite side, then right there where we have Fs, that will represent our adjacent side. So that's why we have force cos angle, because we're using the adjacent and the hypotenuse side. So our force is once again 11 kilonewtons multiplied by 10 to the power of 3 and cos 50. So our shear force is going to be 7.07 multiplied by 10 to the power of 3 newtons. And this will represent our shear force. Now let's go ahead and calculate our shear stress and our tensile stress. So I'll start with the shear stress first. So shear stress, so that's the symbol for stress and a little subscript S to represent shear stress. It's just going to be force divided by area. And we've already calculated our area up top, just as a reminder. That was 113.10 times 10 to the negative 6. So if we do that now for force, that would just be 7.07 times 10 to the power of 3. That's our previously calculated shear force divided by the area that we calculated, which was 113.10, and times 10 to the power of negative 6. And our shear stress now is going to be 62.51, and I'm just going to write this as mega newtons. So that's, or I can just put times 10 to the power of 6, or you could have just written it as mega newton per meter square. So since this is times 10 to the power of 6, it's just newtons per meter squared. If we wanted to, say, rewrite this as mega newtons, then it could just simply be 62.51. And instead of having the times 10 to the power of 6, we just use a capital M there for mega newtons per meter squared. And that right there represents our shear stress. Now for the tensile stress, let's do that now. So that's our stress symbol, a little t for tensile, and it's still just force divided by area. And our tensile force, if we can just recall what that was, it's 8.43 times 10 to the power of 3. So let's do that now. So 8.43 and times 10 to the power of 3, and all divided now, it's going to be divided by the same area as before, which was 113.10 times 10 to the negative 6. The only difference with these two is one of the force is interacting perpendicular to the area, whereas the other is interacting parallel to the area. So for our tensile stress, I'll just write this in as 74.54 mega newtons per meter squared. Now there are some additional nuances to this where a question could go on further to ask you to calculate stuff like the factor of safety, but I've gone a little bit extra with that calculation in this next video right here. So you will see the same sort of steps, but it goes a bit further to calculating the factor of safety. So check that video here, and if you enjoy the content, then please subscribe to the channel and give the video a thumbs up. I'll see you in the next video.